A visitor from outside our solar system just flew past the sun, and based on what our best telescopes just measured, it might be billions of years older than the sun itself, not older by a little, possibly twice as old, possibly old enough that the star it originally formed around burned out and died before our own sun ever ignited. Scientists pointed the James Webb Space Telescope at it anyway, and what came back is stranger than almost anyone expected. A chemical signature that doesn't match anything born in our solar system, and one gas in particular that shouldn't have survived the trip at all. Stay with me, because this is one of the strangest confirmed space stories of the last year, and almost none of what you've heard about it online is the full picture. I'm Jack Henry. This is the channel for real data, not wild guesses. Follow now. We're just getting started. Let's start with the basics, in plain language. Our solar system has one sun, 8 planets, a swarm of moons, and countless smaller bodies. Asteroids, comets, chunks of rock and ice left over from the beginning. All of it bound by the sun's gravity, looping in orbits that repeat year after year for as long as the solar system exists. Every once in a great while, though, something shows up that doesn't belong here at all. Something that formed around a completely different star, got flung out into the galaxy, and is only passing through our neighborhood once, on its way to somewhere else, never to return. Astronomers call these rare travelers interstellar objects. In all of recorded human history, we have confirmed exactly 3 of them. The first arrived in 2017. Small, strangely elongated, tumbling through space in a way that kept scientists arguing about it for years. It showed almost no visible activity, no obvious gas or dust, which made it maddeningly hard to study. By the time telescopes fully grasped what they were looking at, it was already too faint and too far gone to learn much more. The second showed up in 2019, and it behaved far more like a familiar comet. A glowing coma, a visible tail, real cometary activity that gave scientists a much richer data set. But it, too, was already departing by the time the world's instruments were locked onto it. Both encounters left astronomers with the same frustration. Not enough warning, not enough time, not enough data. What they wanted was a third visitor, bigger, brighter, more active, and spotted early enough that the best telescopes on and off the planet could actually prepare. That's exactly what happened next. On July 1st, 2025, telescopes at a survey station in Rio Hurtado, Chile, caught something streaking across the sky. The station is part of the Asteroid Terrestrial Impact Last Alert System, ATLAS, a global network of telescopes built to scan the entire sky every single night, hunting for anything that could threaten Earth. That night, the system flagged a faint, fast-moving point of light. Astronomers checked its trajectory, and within days, they had their answer. This object was moving far too fast to be captured by the sun's gravity. It wasn't going to loop back. It was going to pass through and keep going, out into deep space forever. It was the third confirmed interstellar object in recorded history. It was named 3I/ATLAS, the 3I marking it as the third interstellar object, ATLAS honoring the survey that found it. Almost immediately, something about it stood out. The shape of an object's path around the sun tells you how attached it is to our star's gravity. A path that curves gently and loops back means it belongs here. A path that comes in fast, bends only slightly, and shoots straight back out means it's only passing through. 3I/ATLAS had the most extreme, most sharply hyperbolic path ever measured for an interstellar object, moving at well over 200,000 kilometers per hour when it was first spotted, and accelerating as it fell toward the sun. And here's where the story turns genuinely strange, and why I opened with that line about the sun. By measuring how fast this object is moving relative to the average motion of stars in our part of the galaxy, scientists were able to estimate roughly how long it's been drifting through interstellar space since it was first flung out of whatever star system it originally called home. The earliest estimates, based on its speed alone, placed the age somewhere between 3 and 11 billion years old. Our own sun and solar system, for comparison, are about 4.5 billion years old, which means it was already plausible that this comet predates our star. Then, in mid-2026, researchers went further, using a different method. Measuring the ratios of carbon and deuterium isotopes locked inside the comet's ice, essentially a chemical clock. A team publishing in the journal Nature pushed the estimate even higher, somewhere between 10 and 12 billion years old. That would place its formation during what astronomers call cosmic noon, a period roughly 2 to 4 billion years after the Big Bang, when star formation across the universe was at its most explosive. The universe itself is about 13.8 billion years old. If that estimate holds, 3I/ATLAS isn't just older than the Sun, it's nearly as old as the universe itself. Sit with that for a second. A frozen fragment of a solar system that may have finished forming, lived out its history, and possibly been destroyed before our own sun was even born, drifting alone through the empty dark for 10 billion years or more. Just happened to cross paths with ours, close enough for our telescopes to actually reach out and touch it. Unlike the first interstellar visitor in 2017, which looked mostly quiet and inert, 3I/ATLAS turned out to be a genuinely active comet. As it approached the sun and warmed up, frozen material on its surface began turning directly into gas, streaming outward and forming a glowing coma and a faint tail. For scientists, that activity is everything. A quiet, inactive rock keeps its secrets. An active, outgassing comet hands them over freely, one molecule at a time. It's also worth pausing to appreciate just how much coordinated effort went into finding this thing in the first place. ATLAS scans huge swaths of the night sky every clear night, comparing each new image against the last, hunting for anything that moves. The overwhelming majority of what it catches are ordinary asteroids safely orbiting within our own solar system. Catching a genuine interstellar object is a needle in an almost incomprehensibly large haystack of nightly sky images, and critically, ATLAS caught this one early, months before its closest approach to the Sun. That gave astronomers something they'd never really had before: real lead time. Instead of scrambling at the last second, the way teams had to in 2017 and 2019, space agencies could actually schedule time on some of the most in-demand telescopes on and off the planet months in advance. Before we get into what the James Webb Space Telescope actually found, it's worth talking, briefly, about how it found it. Because tracking this object was harder than it sounds. Webb doesn't see light the way our eyes do. It's tuned to infrared, longer wavelengths that carry heat signatures and chemical fingerprints invisible to ordinary telescopes. That makes it extraordinary for reading the precise chemical makeup of faint, distant objects. But Webb wasn't built with fast-moving small solar system objects in mind, and tracking something moving as quickly as 3I/ATLAS across the sky pushed its systems in ways they weren't originally designed for. Engineers managed it anyway. Webb first locked onto the comet on August 6, 2025, capturing its earliest detailed spectrum, a chemical fingerprint written in light. Then, after the comet swung around the Sun and began heading back out of the solar system, Webb observed it again in mid-December 2025 on the 15th, 16th, and 27th, this time using its MIRI instrument tuned specifically to mid-infrared wavelengths. Those observations produced the most detailed chemical readout ever taken of an interstellar object. What came back surprised a lot of scientists. First, the comet showed an unusually high ratio of carbon dioxide to water vapor. Well outside the pattern typically seen in comets that formed here in our own solar system. That mismatch hinted that whatever environment built this object was chemically different from the one that built the comets native to our neighborhood. Then came the bigger discovery. Buried in the mid-infrared data, scientists identified a clear signature of methane gas streaming from the comet. The first time methane has ever been directly detected coming from an interstellar object. Alongside it, Webb also picked up water vapor and something genuinely unexpected, a distinct atomic signature belonging to nickel. Finding a metal like nickel in the gas escaping from a comet is unusual, and it tells scientists something concrete about the raw ingredients mixed into this object when it first formed, likely 10 billion years ago or more, around a star system that may no longer exist. Here's why the methane matters so much. Methane is a small, fragile molecule. exposed to raw cosmic radiation over long stretches of time. Exactly the kind of unshielded bombardment an object drifting alone through interstellar space for billions of years would experience non-stop. It tends to break down. Scientists didn't expect to find much of it left on the outer surface of something this old. Finding a strong, clear signal was a genuine surprise, and it forced researchers to ask where, exactly, it was coming from. The leading explanation. The comet's outer layers had lost most of their original methane over billions of years of radiation exposure, but what Webb was detecting was methane escaping from deeper, unprocessed material underneath. Material that had been shielded from that radiation the entire time, only now being exposed as the outer layers boiled away in the heat of our sun. There's an added wrinkle here that makes the story even better. Between the December 16th and December 27th observations, Webb noticed that water production had dropped sharply, even as methane and carbon dioxide stayed active. The comet had crossed what astronomers call the snow line, the distance from the sun beyond which temperatures are cold enough for water vapor to freeze back into ice. Water shut down. Methane and carbon dioxide, which need far less heat to stay active, kept going. In other words, Webb wasn't just reading the surface of this ancient visitor. It was reading straight into material that had been locked away, untouched, since before our own solar system existed. And it caught the moment, in real time, when different layers of that material switched on and off. That's genuinely one of those moments worth stopping to appreciate. A team of scientists pointed a telescope at a fast-moving speck of light, and that telescope read out the actual chemical ingredients of a piece of another solar system. Ingredients that had been frozen and hidden for billions of years, untouched until that exact moment. Webb wasn't the only instrument on this. NASA's Hubble Space Telescope observed 3I/ATLAS shortly after its discovery and again after it passed the Sun, giving scientists their first estimates of the size of the comet's solid nucleus buried underneath all that glowing gas and dust. As the comet's activity settled down after its closest approach, later observations let researchers separate the faint glow of the solid core from the much brighter coma surrounding it. Estimates for the nucleus size shifted as more data came in, which is normal. From a telescope's point of view, the tiny solid core is almost always drowned out by the cloud around it, and astronomers have to model brightness across different wavelengths, combined with assumptions about how reflective the surface material is, just to separate the two. The most refined measurements put the solid nucleus at roughly a kilometer or more across, noticeably larger than either interstellar visitor before it. That larger size is part of why 3I/ATLAS became so much brighter and easier to study. More surface area means more material heating up and releasing gas, which means a richer coma and a stronger signal for instruments like Webb to lock onto. Other instruments joined the effort too. CSFX, a space telescope designed to survey the entire sky in infrared, observed the comet in December 2025 and picked up signs of increasing activity after perihelion, along with dust made of tougher, more heat-resistant material and additional gas signatures. Ground-based radio telescopes using the ELMA array in Chile detected still more molecules escaping from the comet, including methanol and hydrogen cyanide, with methanol showing up in unusually high abundance relative to hydrogen cyanide, another chemical fingerprint pointing toward an environment very different from our own solar system's formation history. Later still, spectrographs on the European Southern Observatory's Very Large Telescope added nitrogen isotope measurements that supported the same conclusion Webb's carbon data had already pointed to. This object's raw chemistry doesn't match anything born around our sun, because 3I/ATLAS moved on such an extreme path. And because it turned out to be larger and older than expected, some corners of the internet ran wild with speculation. Theories that it might not be natural at all. That reaction isn't unreasonable on its face. When something unusual shows up from outside our solar system, it's a completely normal human impulse to wonder what else it could be. Scientists took that seriously enough to actually check, rather than just dismiss it. Researchers pointed radio telescope arrays specifically designed to search for technosignatures, artificial radio signals that might suggest something built rather than formed naturally, directly at 3I/ATLAS during its passage through the solar system, listening across a wide range of frequencies. The result was clear: no artificial signals of any kind. Every instrument, from Webb's chemical fingerprint to Hubble's imaging to the dedicated radio searches, points to exactly what an ancient natural comet should look like. Its behavior matches known cometary physics. Its chemistry, while unusual, fits within the range scientists expect from an icy body that formed around a different star. Its coma, its gas emissions, its dust, all of it lines up with a natural object, not anything constructed. None of that dismissal is needed to make this story remarkable, either. A confirmed visitor from another solar system, conceivably older than the universe's midpoint, carrying chemistry frozen since before our sun existed, studied directly by our most advanced space telescopes. That's already one of the most extraordinary natural discoveries of the decade. It doesn't need embellishment. The verified truth here is stranger and more grounded than the rumors ever were. So what does any of this mean for the rest of us? Every interstellar object we get the chance to study up close hands scientists a genuine physical sample of material built around a star system we will likely never visit or directly observe in detail. Instead of only theorizing about distant star systems based on faint light readings, an interstellar object lets researchers directly measure the raw ingredients that built planets and comets somewhere else entirely in the galaxy. That's an extraordinarily rare opportunity. We've only had 3 chances like it in all of recorded history, and 3I/ATLAS gave scientists by far the richest data set of the 3, largely because of its size, its activity, and the sheer amount of advanced instrumentation trained on it compared to what existed back in 2017. There's a bigger picture forming here, too. For a long time, astronomers debated whether interstellar visitors like this were rare, one-off flukes, or whether space is actually full of them, quietly drifting past undetected simply because we lacked the tools or the timing to catch them. Confirming 3 of these objects within less than a decade, with detection technology still improving every year, suggests these wanderers might be far more common than anyone originally guessed. That trend is about to accelerate. A newly operational ground-based survey telescope, purpose-built to scan the entire visible sky every few nights with extraordinary sensitivity, recently began full science operations in Chile, and many astronomers expect it to dramatically increase how quickly future interstellar objects get identified after entering the solar system. More warning time means more opportunities to line up instruments like Webb and Hubble well in advance, the same way teams did with 3I/ATLAS, instead of racing the clock the way they had to with the very first visitor back in 2017. It's also worth appreciating the sheer scale of global cooperation this one comet required. The initial detection came from a ground-based survey network. Confirmation and orbit calculations involved observatories on multiple continents comparing notes within days. Space telescopes from different national agencies took turns studying it from orbit, each contributing a different piece of the chemical puzzle. Radio arrays added detail from an entirely different part of the spectrum. Quietly, in the background, teams around the world shared data and coordinated schedules toward one shared goal: understanding this one ancient visitor as completely as possible before it disappeared from view for good. Take a moment to sit with the full timeline of what this comet has actually been through, because it's easy to skim past the scale of it. This object formed somewhere between 10 and 12 billion years ago, around a star that may not exist anymore, in a region of the galaxy we'll likely never see in any detail. At some point in its ancient history, researchers now think it may have been torn loose not by a violent planetary ejection, but by the gentler gravitational pull of a passing star, given how far its formation site appears to have been from any active planet-building region. It was flung out of that system entirely, sent drifting alone through the emptiness of interstellar space. No star to orbit, no light to warm it, just cold and silence for billions of years. Then, purely by chance, its long, silent journey brought it close enough to our sun for our solar system's gravity to finally bend its path, and close enough for our telescopes to catch it. It swept past the sun, warmed just enough to release some of that ancient frozen material, giving our instruments a brief window to read its chemistry in real time, and then it continued outward, heading back into the depths of the galaxy, likely never to return. Weigh that against the scale of human history. Telescopes themselves have only existed for around 400 years. Space telescopes capable of reading a comet's precise chemical fingerprint have only existed for a few decades. Out of the 10+ billion years this object spent drifting silently through the galaxy, it happened to pass close to our Sun during the exact narrow sliver of human history when we had both the knowledge to recognize it as interstellar and the technology to study it in real time. A few hundred years earlier, it would have been nothing more than an unexplained smudge of light in the sky. We happened to be alive, with the right telescopes pointed at the right patch of sky, during the one brief moment this ancient traveler passed close enough to notice. That's an extraordinary piece of cosmic timing, and it took real, sustained, global effort to make the most of it before the comet faded from view for good. Findings from 3IATLAS have already been formally published in Nature and other leading journals, cementing its place as the most thoroughly studied interstellar object humanity has ever encountered. And by this spring, as the comet drifted outward past Jupiter's orbit, Webb was still scheduled for one more look before the object became too faint to observe at all. To bring it all together, in the summer of 2025, a fast-moving object was spotted crossing our solar system, and within days, scientists confirmed it wasn't from around here at all. It was the third confirmed interstellar object in recorded history, and it turned out to be one of the most extreme ever measured. The sharpest, most hyperbolic path ever tracked. The best current estimates place its age somewhere between 3 and 12 billion years old, with the most recent isotope-based research favoring the older end of that range. Old enough that it may have formed before our own sun existed, possibly even before most of the stars in our galaxy's disk had finished forming. As it swept past the sun in the fall of 2025, it heated up and came alive, releasing gas and dust that our most advanced telescopes could finally study directly. The James Webb Space Telescope captured detailed chemical readings showing unusually high carbon dioxide, the first ever direct detection of methane from an interstellar object, clear water vapor, and a rare atomic signal from nickel, all pointing to chemistry that almost certainly formed in a completely different star system than our own. Hubble helped pin down its size. SPHS and ground-based radio telescopes added even more chemical detail. And a dedicated search for artificial signals came back completely clear, confirming this is exactly what it appears to be: a genuine, ancient, natural piece of another solar system, passing quietly through our own before heading back out into deep space, likely never to return. That's the real story, backed by real data, from real telescopes, gathered by real scientists working together across the globe to make sense of one extraordinary visitor. And it's stories like this one, grounded entirely in verified science, that this channel exists to bring you first. Follow now if you haven't already. Drop a comment telling me what part of this surprised you the most. And share this with someone who'd find it as fascinating as you clearly do. We'll see you in the next one.